So before you begin this lesson, make sure that you've watched the videos on matrix multiplication and addition. We're going to be looking at 2.2, the theory of matrix algebra, but I'm not really going to go into depth on the multiplication and addition of matrices. Instead, we're going to be looking at what happens when we start to think about matrices more globally and we want to learn some of the principles or rules of matrix algebra. Okay, so let's take a look and let's first take a look at a class of matrices. Okay, these are going to be diagonal matrices in which what we're going to do is we're going to have a non we're going to have only values along the diagonal, and we're going to start out with the identity matrix. Okay, so we've got the identity matrix and we're going to start out with I, and let's say for example I have I3. So I3 is going to be 1 0 0 0 1 0 0 0 1. Okay, and what I'm going to do with this matrix is I'm going to say, okay, well, why is it called the identity? For what reason? What makes it an identity matrix? And so what makes it an identity is this is the identity for any matrix with 3 values in its column. Okay, and we're going to see in a minute why it's got to be 3 values inside of the column. All right, it transforms or multiplies back to the original matrix. And so let's see what that looks like. So let's say, for example, I take 1 0 0 0 1 0 0 0 1, and I'm going to multiply that now by, let's say, for example, we'll take this 3 by 2 matrix, okay, and it's got 2 1 1 0 3 1, okay, and we're going to do some multiplication with that. So we'll have 1 times 1 times 2 is 2, plus 0 times 1 is 0, plus 3 times 0 is 0, so that gives me 2. Okay? Then I'll take 1 times 1 is 1, and 0 times 0 is 0, and 0 times 0 is 0, so this becomes 1. Okay? Next up, I'm going to have 0 times 2 is 0, 1 times 1, right, is 1, 0 times 3 is 0, so this becomes a 1. So all I'm doing is multiplying here. Then I'll have 0 times 1 is 0, so we'll do the next one. 1 times 0 is 0, 0 times 1 is 0, and so that gives me now 0. Then we'll have 0 times 2 is 0, 0 times 1 is 0, 1 times 3 is 3, so when we add those all together we get 3. And then we'll have 0 times 1 is 0, 0 times 0 is 0, and 1 times 1 is 1, and we get 1 back. Okay? So basically what we've done here is we've actually gone in, we've used matrix multiplication, and we've shown that if this is I3, and we multiply it times B, okay, right, what I get back is B, okay? And that's the idea of an identity. Now, we see identities a lot. They show up a lot we've seen them in, say, for example, working with the real numbers. 1 is an identity. It's called the multiplicative identity, right, because you multiply anything by 1 and you get 1, or you get the number back, excuse me. So like 3 times 1 is 3, or 4 times 1 is 4, etc., etc. On the other hand, we also have something called an additive identity, and that's 0 when we think about the real numbers, because any number plus 0 is itself, right? That's the whole idea of an identity. An identity, when we do an operation to an object inside of a set, right? If it gives us back the original object, then what we have there is an identity. That's what it means to have an identity. So for example, all right, let's take, for example, we'll take I2. So we got 1, 0, 0, 1. Okay, we've defined that. It's got 1s along the diagonal, 0s everywhere else. And I'll multiply that now just by another matrix. We'll call it 2, 1, 3, 1. Okay, and what we see is we'll get 1 times 2 is 2, and 0 times 3 is 3. So this is 2 plus 0. Okay, first element. Then we'll go 1 times 1 is 1, 0 times 1 is 1, so 1 plus 0 again. Then we'll have 0 times 2, right? 0 plus 1 times 3 is 3. And then we'll have 0 times 1, right, is 0, plus this 1 times 1 is 1. So that's now going to give me 1. And so what I get here is I get 2, 1, 3, 1. And that's the idea behind the identity. The identity, what will happen is that if we multiply anything by the identity, it gives us back the original value or the original matrix. Okay? So if we wanted to generalize, if, okay, and we're going to be very careful about this in just a minute, if A is n by m, then in times A equals A. Right? That's the identity. Now, you'll notice that it's going to be n by m, and what I've got here is I've actually noticed that I've actually put the same number of, in this case, columns in the identity is equal to the number of rows in A, okay? And that's going to get to our second point here, okay? Because let's take a look. Let's say, for example, I did the opposite way around, and we're going to use a different example. We'll let A, in this case, equal this vector 1, 3. Okay, we got A equals 1, 3. And we'll use now I2, the identity, which 2 by 2 identity, 1, 0, 0, 1. And let's see what happens when we do A, I2. So I'm going to do that. And what I've got 1, 3, and I'll multiply it by 1, 0, 0, 1. And I get 1 times 1 is 1, but I have a problem here because I need a second value, okay? I need a second value. I'm supposed to do rows times columns. 1 times 1 is 1, but then what am I going to multiply by 0? I don't have anything to multiply by 0. Okay, when I do multiplication, it's supposed to be I multiply the row, right, times the column. Row in A times the column in I2. But there's not enough, right? But there are not enough elements in A to allow us to do that. Okay, so we actually can't do that, and I think I talked about this a little bit inside of the video. But let's talk about under what conditions can we actually do multiplication. Right? We notice here that if I take I2 times A, right? If I did it this way, okay, I2 times A is going to equal just A, because A is the right number. We can actually see that, right? I'll show you. I got 1, 0, 0, 1. And I multiply this now by 1, 3. And what I get is 1 times 1 is 1, 0 times 3 is 0, so this ends up being 1. And 0 times 1 is 0, 1 times 3 is 3, so this ends up being 1, 3. So I ended up with I2 times A equals A. But it doesn't work the other way around because basically, well, A is the wrong dimension or I2 is the wrong dimension. Okay? The question is, how big would I need for either A to be or I2 to be in order for me to actually be able to multiply? Okay? So let's ask that question. Let's take a look at that and we'll ask that question. So under what conditions may we multiply two matrices together? Okay? So under what conditions can this actually happen? Well, first, let's take a look. And what we want to notice is we're going to multiply. We multiply rows times columns. Rows in the left matrix times columns in the right matrix. Okay? So rows in the left matrix times columns in the right matrix. So if we look at something like, say, for example, like this, we got 1, 0, negative 3, 2, and I want to multiply it now by, in this case, say, for example, 1, 4. the vector 1, 4, I can do this because I can take 1 times 1 and 0 times 4, okay? And that'll end up giving me, right, 1 plus 0. And I can take negative 3 times 1 and 2 times 4. So I end up with negative 3 plus 8. So that actually works too. And I end up with 1, 5 as my resulting vector, 1, 5. Okay? So that actually works, right? And what we want to notice here is that what we have is we have the same number of columns in A as the number of columns in B. The number of rows in B. Okay, the number of rows in B. All right, so we notice that that's going to be the case. Let's take a look at another example. All right. So now what we'll do is we'll see, okay, so I got to take 3 times 1. That's 3 plus negative 1 times 2. That's, so we got 3 plus negative 2 plus 0. That's going to be the first row, first column. And then we'll have 0 times 1, or excuse me, we'll have 3 times negative 2, so that's negative 6 plus negative 1 plus 0. That's the second. Then we'll have 0 times 1 is 0 plus 2 plus 3. Then we'll have 0 times negative 2, that's 0. 1 times 1 is 1 plus 3 times 1 is 3. Then we'll have 5 times 1 is 5 plus 2 times 2, so we have 5 plus 4 plus 0. And then we have negative 10 plus 2 plus 1. And what we end up with is we end up with negative 1, negative 7, 5, 4, 9, and negative 7. And that's our resulting matrix when we matrix multiply. Now what we want to notice here is the number of columns in A in this one, the left one, okay, is the same as the number of rows equals the number of rows in the right one. Rows in the right matrix. On the other hand, what if we flip them around? Well, if you think about it, if we flip them around, what you'd see is that now we'd be trying to multiply a row vector, okay, this row vector, 1, 2, say 1, negative 2, times the column vector 3, 0, 5. But that doesn't work, okay? So if we flip them, we'd end up with something that wouldn't work, right? Because we'd be trying to take the dot product of two vectors that are not the same size, right? By flipping the matrices, we would be trying to take the dot product of two matrices that are not the same size. Of two vectors that are not the same size. And that's not possible. So let's think about the dimensions and what the dimensions would have to be for us to actually be able to do any kind of multiplication, right? For us to be able to do any kind of multiplication, we're going to have some special properties or special property. All right, so to multiply matrices together, there must be the same number of columns in the left matrix as rows in the right. In other words, for us to be able to do AB, okay, right? For AB to be possible, A must be All right, if it's n by m, and b would then have to be m by p. Okay? So basically what we're saying is that the second value in terms of the dimensions, that's the number of columns in A, and B must be, m by P, all right? So what we need to have is we need to have on the left-hand side, we're going to need, we'll have an m by m, so they could be any size that we want, but B is then going to end up being m by P, okay? The resulting matrix is then going to be n by P. N by P. Okay, it's going to be an m by P, all right? So we could take a look actually up here. Let's go back to our previous examples. If you see here, we'll start with this first one. We took a 2 by 2, okay, times a 2 by 1, all right? And what we ended up with is we ended up with a 2 by 1. So these two said we can multiply, and these two said, okay, the size of the matrix, or the dimensions of the matrix. All right. The second example, right? We've got a 3 by 3 times a 3 by 2. Okay, so these two are the same. That tells me that they can in fact multiply. That says I can multiply. And these two, they tell me the dimensions of the resulting matrix of the result are 3 by 2. So if, say for example, we'll take some examples, A is 3 by 1, and B is 1 by 7, then AB is 3 by 7. Notice 1 and 1, okay? We've got the inside values, the inside dimensions are the same, and the outside dimensions are going to give us the size of the matrix. Okay, that's 1. Let's say, for example, A is now 2 by 5, and B is 3 by 5. Then the two matrices cannot be multiplied together. AB, okay, because if you notice, those two are not the same, or BA even. So if we went the opposite way, we couldn't do that either, because what you'd see is that you'd end up going 3 by 5 times 2 by 5, and we'd still not have the inside values be exactly the same. Okay? Or, say for example, we have A is 4 by 6, and B is 3 by 4. Okay? So AB is not possible, but BA, right, we see that the 4 and the 4 are the same, and then these will actually be the exterior. So what we'd have, BA would be 3 by 4 times 4 by 6, and its result would then be 3 by 6. That would be the resulting size of the matrix. So this kind of describes for us how it is that we could actually, in fact, do matrix multiplication. All right? We can only do matrix multiplication if, when we are multiplying, our left-hand side matrix has the same number of columns as the rows in the right-hand side matrix. All right? Otherwise, we're not going to actually be able to do the multiplication. Now, if you're doing your multiplication correctly, you'd see, nope, can't do it. It's not possible. Or, yes, I can. And then you would get the exact number that the exact number of components inside of the matrix, the exact size that we want. But thinking about it from this perspective is going to make life a lot easier for us as we start to think more abstractly about matrices, as we think about linear transformations and we think about vectors. okay? Because it's going to actually allow us to make certain generalizations, certain really powerful generalizations, okay? So the next question we want to answer is, are matrices commutative under multiplication? The fact of the matter is that we do know, okay, and I'm going to tell you this, that matrices are commutative under addition, right? Well, what does that mean? What does that mean? That means, okay, A plus B equals B plus A, as long as we can actually add A and B. But is AB equal to BA? Okay? In the real numbers, we know that that's true. In the real numbers, we're like, hey, no problem, of course. 3 times 5 is the same as 5 times 3. But is that true for matrices? Our immediate thought, actually, if we just kind of understand what we just did, the fact of the matter is that no, it's not. Okay? So suppose, right, that A is 3 by 5, and B is 5 by 7. Well, AB, its resulting matrix, results in a matrix, right? We've got 3 by 5 times 5 by 7, and that'll equal a 3 by 7. Great. But BA cannot even be multiplied. So that's not even going to work. We're not even going to be able to multiply the two of them together because, okay, what we get is we get that BA is 5 by 7 times 3 by 5, and so the number of columns in B are not equal to the number of rows in A, so no good. That doesn't work, right? So our immediate impression is, yeah, no, I mean, if we don't even have the right size, we're not actually going to be able to multiply, okay? So we'll ask ourselves, what size of matrices will we need in order to actually be able to commute? So in general, matrices are not commutative because generally we often cannot even multiply in a different order. Well, sometimes though we can, right? So suppose, right, that B is 3 by 4 and A is 4 by 3. So if we look at AB is going to be 4 by 3 times 3 by 4. So that can be multiplied. And BA is 3 by 4 times 4 by 3. Okay? So that can also be multiplied. But the result, okay, in the case of AB is going to end up being 4 by 4. And the result in the case of BA is going to be 3 by 3. So that doesn't work. Okay? Clearly, AB does not equal BA because they're not even the same size. They are not even the same dimension. So it begs the question, under what conditions might we actually have AB equal to BA? So when will BA and AB actually be the same size? Okay? And so that's only going to happen when A and B are both square, okay, and well, are both square in the same dimensions. So if A is n by n and B is n by n, then AB is n by n, right? Because you'll basically, your outsides will end up being the dimensions, and the insides will be the same, so that we can actually do the multiplication. And BA is n by n. But does that mean that we have that AB equals BA? Is that the case? Okay. And let's check it out. Let's see an example to see if that actually is the case. Because if we find one example in which it's not true, we're good to go. We actually have shown that, in fact, the two are not the same. So let's take two of them. We'll let A equal, okay, 2, -1, 3, 1. Okay, and we'll let B equal 5, 0, 1, -2. All right, so AB is going to equal 2, -1, 3, 1 times 5, 0, 1, -2. And this is then going to equal, we got 2 times 5 is 10, -1 times 1 is -1, so this is going to end up giving me 9. And then 2 times 0 is 0, -1 times -2 is 2. Great. Then 3 times 5 is 15, 1 times 1 is 1, so that gives me 16 when I add the two of them together. 3 times 0 is 0, 1 times -2 is -2. Okay? So that's AB. Let's see if BA actually was the same thing. So now we'll take BA, and BA is going to be now 5, 0, 1, -2, 2, -1, 3, 1. And that's now going to be, that'll be 10 plus 0, so this is now 10. Uh-oh. We can already tell that the two are not going to end up being equal to each other. Let's finish this up. 5 times -1 is -5 and 0. Okay. Then we'll have 1 times 2 is 2. Minus 6 is -4. Okay. And then 1 times -1 plus -2 times 1 is -3. And you'll see here that AB now does not equal BA. Okay? So even though we actually have matrices that are in fact the same size, it's not going to work. We're not going to end up having commutative matrices. It's not going to work. All right? They're not going to commute. And so that actually tells us that multiplication, right, is not commutative. You cannot multiply in any order that you want. So multiplication of matrices is not commutative. In general, okay? Now, it doesn't mean that it doesn't happen. You actually can have commutative matrices, right? Two matrices that actually do commute. But in general, we say that AB does not equal BA. Okay? So, like, for example, a good example of something like this is, let's say, for example, we take A plus B and we square them. Okay? And A and B are matrices in this case. Now, if we think about it like, oh, that's a perfect square trinomial, right? Shouldn't that be A squared plus 2AB plus B squared? Well, we have a problem. What we do know is that this is going to end up being A plus B, right? And let's assume that you can, in fact, multiply A and B. Let's say that they're both n by n matrices, right? That is that, right? We'll let A and B are n by n. That is, they're both square, so that this actually can happen. So now, right, we're going to actually have A times A. This will end up giving me something called A squared, which is just A times A, plus, that's my outside, plus AB, then plus BA, okay? Plus BA, and then plus B squared. So what we see here is we do have this all that multiplication done, but we cannot. These are not the same matrices. So they are not 2AB. They're not 2AB or not 2BA. Okay? They're literally AB plus BA. You've got to actually keep it exactly like that. Right? We cannot change that up. And that's going to end up becoming really really important as we talk more generally about matrices, because we're going to be doing different things with these matrices. And what you're going to see is like, if you assume commutativity, you get one result, but in other cases, right, if you assume that that the two are not commutative, you get a different result. And that's really key. That's really important. So when we have AB, we're going to say that B is going to be left multiplied by A, or A is right multiplied by B. We're actually going to define on which side we're going to be doing our multiplication of matrices, right? And if I say AB, I literally mean we are left multiplying B by A, or we are right multiplying A by B, okay? So AB, not BA, okay? It matters the direction. On the other hand, there are some things that actually kind of show up that are very similar, all right? Or at least some properties that are the same as they were in working with the real numbers. So we've got some properties of matrices, right? We have one, it's called associativity, okay? You don't need to know it's called associativity. You probably have an idea. A, right, times B times C. So if we multiply BC first and then left multiply by A, then that's going to be the same as multiplying AB and then right multiplying by C, okay? So basically we can multiply in any grouping that we want. That doesn't mean any ordering, it just means groupings, right? We can multiply, right, one set first and then right multiply by the third set, okay? Or we can multiply the second and third matrices and then multiply by and then left multiply by the first, okay? We also have a distributivity, okay? And that's A times B plus C is going to equal AB plus AC. And remember, the ordering is going to matter a lot. That's distribution, okay? Basically a distributivity. 3, we can also do A plus B times C, okay? And what you want to notice is that this is not the same thing as 2, right? Because on the one hand, for 2, we're left multiplying, but on the case for 3, we're going to right multiply. So this is going to end up being AC plus BC, okay? And notice that the number that we're now the matrix that we're going to be multiplying or distributing, C in this case, is now on the right side, okay? So notice, right, different sides. Very important. Okay, we're going to end up with different sides in which we're going to be multiplying, right? So while it looks very similar to the real numbers, that positioning of the matrix when we multiply it is really crucial, and it actually ends up giving us. Let's take a look at these results now. We're going to take a look at some results for transposes, and we're going to do these without proof with regard to this for this class. So first, we've got A transpose. If we take A transpose and we transpose it again, we're going to end up back at A. Pretty intuitive, right? It's basically like if the transpose of a transpose is the original matrix. All good. Now, the transpose also what we can distribute the transpose over addition. So A plus C transpose is A transpose plus C transpose. And we can also distribute the transpose over multiplication, but it's going to be a little bit different, and this is going to show up quite a lot. What we're going to do is we'll transpose the individual matrices, okay, but then we're going to have to change their order. And remember, because we're working with matrix multiplication, order matters a lot, okay? So consequently, AB transpose, right, is going to equal B transpose, A transpose, and we'll actually end up doing that switching, the switching of B transpose and A transpose. If you're interested in actually looking at the proofs, there are some proofs inside of your book, okay, that you can take a look at to see how it is that we found these particular results. What we're going to do is we're going to use these results to do some proving work, okay? So we'll do some work with proving. So let's prove that if A and B are symmetric, n by n matrices, such that AB equals BA, then AB is symmetric. So what we're going to do, we want to think about, one, what does it mean to be symmetric? All right, and then what does it mean that AB equals BA? That basically is that the two are commutative, which we said is very strange. It's just different. Then AB is symmetric. Its result is in fact symmetric. All right, so I want to think about what does it mean for A and B to be symmetric, and also AB to be symmetric. So A is symmetric if A transpose equals A, so we know that, and B is symmetric if B transpose equals B. So we know this is true. What we want to prove then, we want to prove that AB transpose equals AB, because that would then actually end up giving us our result that we want. Okay, now I'm going to kind of move backwards a little bit because I do have some rules about or properties of the transpose that are going to help me think about this. Right? I'm not going to start my proof yet, but I am going to at least think about this result here, okay, to help me think about how I'm going to end up doing my proving later on. Okay, so AB transpose. Well, AB transpose is going to equal B transpose A transpose. Okay, and when I look at this, what I see B transpose A transpose, starting at the end, is going to end up equaling, well, B transpose is B, right? That's the true statement. And A transpose is A, so this ends up equaling BA. And then I have also originally that AB equals BA, so this is going to end up being AB. Ta-da! There we go. Okay? And so consequently, what I see here is that I can actually just utilize some of these properties to go from basically my result, right, to getting B transpose or AB transpose equal to AB. Okay? So I kind of like started at the end and then moved backwards. Now to write my proof out, I'm not going to do that, okay? But what I'm going to do is I'm going to first start out with my givens, all right? So I'm going to suppose that A and B are symmetric such that AB equals BA, okay? Then what I'm going to do now is I'm going to take 2, okay? I'll have that AB transpose, okay, is going to equal B transpose, A transpose, and that's one of those properties of transposition. This is a property by a property of transposition. You don't actually, in most of the time, we don't actually have to state that it's going to be a property, but that's just to help you out seeing what it is that I'm doing. All right. Then we have 3 that B transpose, A transpose is going to equal BA, okay, by our given, because A and B are symmetric. And then what we're given next is, right, by our given as well, BA equals AB, okay, right, by assumption. It's by one of our assumptions earlier on. We said that, in fact, they're commutative. Are matrices always commutative? No, they're not, but we did say that in this case they were. So, 5, okay, AB transpose equals AB. And so AB is symmetric. And that's it. What we've done here is we basically utilized some properties of transposition, all right, and the given information that we have about the matrices, and what does it mean to be symmetric in order to actually go out and prove this statement. So if A and B are both symmetric, right, and we have that they also commute, then what we get is we get that result is also going to be symmetric. All right, so what about this one? Let's prove that ABC transpose is going to equal C transpose, B transpose, A transpose. Well, if I look at this, you might say to yourself, wait, that's just a property of transposition, right? AB transpose is B transpose, A transpose, right? We do know that, okay? We have this. This is true by properties of transposition, all right? So why not just say that it's the same for 3 of them? Well, it's because we do math. And in math, we're kind of picky about those kind of things. Why is it that you would expect that if it works for 2, that it is going to work for 3? That doesn't work. You're going to have to go out and prove it. Prove that it'll actually work for 3. So let's do that, okay? But we still can, and it's not an impossible thing to do, okay? What I'm going to do actually here is I'm in fact going to go in and I'm going to kind of, I'm going to go in and I'm going to kind of break things up. And I'm going to say, okay, first, right, that A, B, C transpose is going to equal A times BC transpose by associativity. That's our associative principle. That is that I can group them in any way that I want. And we saw that. That's associativity, okay, which is great. Well, now what I'm going to do is I'm just going to treat BC, okay, as its own matrix, right? One solid matrix, and A as a separate matrix that's going to be left multiplying by BC. Well, now if we think about that, that's actually going to then be that BC transpose, and that's together. Now notice we didn't actually separate it out. We're just going to say it's going to be BC transpose times A transpose, okay, is going to equal this A BC transpose, okay? And that's by a property of transposition, okay? That's like distributing transposes over multiplication. So what we did was we treated the BC as a single matrix, all right? And then we just said, okay, well, if BC is a single matrix, I do know with 2 matrices, right, I have this property right there, okay? Well, now what that means is that BC transpose, A transpose, is simply going to equal C transpose, B transpose, A transpose by properties of transposition. Okay? And what that means is basically, well, I needed first, okay, to separate them into two matrices, okay, that could be multiplied together, utilizing that property of transposition. But once I did that, then I could treat BC now as two matrices, okay, and use their properties of transposition in order to switch the order, okay? And so what that gives me, that's the end of my proof. I'll actually put this over here. That's the end of my proof, okay? And I just utilize those properties of transposition in order to prove what it is that I wanted to prove, okay? So essentially what we're going to be doing with some of these proof things, and it is challenging, it's tricky to do, is you're going to take a look at all those properties that you have, all those things that you've either proven previously through problems or that we've gone over here at this time, and you're going to then use those properties in order to go out and do a little bit of proving, to prove some specific statements. Just be really careful. When you're going through and doing that kind of proving, be careful that you're not taking something for granted, that you're not assuming a result, right, without actually proving it. Only utilize those properties of transposition or multiplication or the things that we know about a particular matrix or kind of matrix, right, in order to do your proving and act as definitions, right? Or you can also utilize the definitions that are given to you, right? For example, if they said, all right, we call this particular matrix a scalar matrix, right? Prove that it has X, Y, and Z property. You can utilize the definition of a scalar matrix, okay? Try not to skip steps. Try not to skip portions here because math is very logical, very detail oriented, and kind of finicky, all right? And we want to get a little bit better at that kind of thing. All right, so this finishes our big overview section on matrix algebra. Matrix algebra is a little bit mind-bending, all right, at first when you start working with it. Just remember, right, don't take anything for granted. Don't assume that it works like the real numbers. Work off of the properties and work off of the restrictions on those properties that we've been discussing. Because if you don't, you're going to end up with results that are simply not true.